Hello class, here is your online lecture on ultrasound, also non-destructive testing or non-destructive examination. So let's talk a little bit about the devices that we use for this. So it says here, ultrasonic measurements utilize piezoelectric transducers. So we already studied piezoelectrics. We know how those work. We know what a transducer is too. That both is an actuator that generates the signal, and then it's a sensor that senses the signal. So that's what this next part says. The device, 1, transmits high-frequency sound waves, and 2, senses the reflection. So since it does both, it's a transducer. Usually piezoelectrics are used for this. Then the ultrasound term. So ultrasound waves refer to anything that is greater than 20 kilohertz. And 20 kilohertz is the upper limit of what humans can hear. So like with light, how we'll say ultraviolet, we use that ultra to refer to waves of frequencies higher than what humans can perceive. We're doing that same thing here with sound. So ultrasound waves are waves that are greater or higher frequencies than what humans can hear. Again, the sentence says kind of what we said above at first. It says make the transducer by using a piezoelectric crystal and then oscillating it with an applied sinusoidal voltage. So these are essentially pulses, but if you remember from our spectral analysis, pulses and all signals are made up of sinusoids. Now we're going to learn a little bit about the sound waves. At the top of the slide, we have a tuning fork. It's excited. So as it vibrates, it moves forward and it compresses the medium. And then it moves, so when it compresses, it makes a moment of higher pressure, or we call them compressions. So areas of higher pressure. And then as it moves back, there are the troughs of those waves, which we call rarefactions. These would be longitudinal waves, and here we see those on the left side of the slide. The oscillations occur in the same direction as wave propagation. There you see that compression moving to the right. This could also be visualized, say if you took a slinky and you kind of pumped it back and forth in the direction of the axis of that slinky. So you're creating those compression and rarefactions, and they're traveling to the right. Those oscillations are in the same direction as the wave propagation. Those are longitudinal waves, and then in comparison, we have transverse waves. And here, the definition is oscillations occur perpendicular to wave propagation. We see that happening there, and it's probably easiest to see it at the bottom, though, where we have the slinky. Essentially here, it's being shook up and down. When you would make, so you would make measurements using longitudinal waves and using transverse waves, sometimes both of them at the same time. I'll mention you need to have couplants. We're going to learn about impedance mismatches or changes in impedance. That's what reflects the sound back. And when we put our transducer up against what we're trying to measure, we need to have a couplant. And with the longitudinal waves, usually glycerin is used. And the main point there is to fill the voids between the transducer and what you're trying to measure. It sort of acts as a transformer. It gets rid of that impedance mismatch that you would have had with the air in between. Then with the transverse waves, you need, usually an adhesive is used. It's more that you need something that's going to stick to it, so when it shakes perpendicular to the wave propagation, it sticks and shakes it. So this slide here shows the steps of pulse echo ultrasound. First, we start with the actuator function of the transducer. So there it's emitting a sound wave, a pulse. So it goes out, and this yellowish orange line here is indicating a change in impedance. So change in impedance, often you can think of this as just a significant change in density. Like say you're going from a solid to air or from air to liquid. These big changes in density, it creates an impedance mismatch, an acoustic impedance mismatch, and that reflects the sound back. Some of it will transmit through, a lot of it will get reflected back. How much depends on the change in the impedance. So here in B, where that change in impedance is reflecting back a significant amount of the energy. And in C, we see it returning to the transducer where it gets sensed. Now here we just have some notes about pulse echo ultrasound. So the first one, medical ultrasound uses frequencies as high as 30 megahertz, and the speed of sound in tissues is about 1,540 meters per second. Just for reference, the speed of sound in air is 343 meters per second, roughly. So it's about 5 times as fast in tissue as it is in air. Crack detection uses waves up to about 10 megahertz. Here we have the speed of sound in solids between 3,000 and 8,000 meters per second. So 10 to, well, not quite 30, but significantly higher speed of sound than through air. Next note, higher frequencies are better for thinner materials. The lower frequencies can be used for thicker materials. You have more space for that wave to develop. Reflections occur at discontinuities in mass density, or changes in acoustic impedance is another way of saying that. Both longitudinal and transverse waves can travel in solids. Transverse waves can't move through air. Longitudinal can move through fluids and solids, but solids allow both longitudinal and transverse waves. Last point here, for standard pulse echo, the wave must travel 2 times the distance between the transceiver and the feature. That feature is the density change or the change in acoustic impedance. Often you might be looking for a crack. So say you're measuring the thickness of an airplane wing. The sound wave needs to travel through it. When it reaches the other side, it comes back. So it travels that distance twice, and that would be the normal. You could get the normal thickness from the time it takes, but just remembering that it's the time, what you measure is the time that it takes to go through that twice. We'll think about that a little bit more in an example we'll do here soon. Something you might have thought of when you thought of ultrasound measurements would be what we call an ultrasound, say when a woman is pregnant. So the main reason why this slide is here is just to point out that to point out a huge advantage of ultrasound measurements, and that is that it allows non-destructive testing. So obviously you can see the benefit there when you're trying to measure a baby. And that same advantage is very useful in other things. You don't necessarily want to tear an airplane wing apart or tear your welding joint apart to see if there are any cracks in it. I thought I'd just throw this slide in. So this last one, that is what was available for many years. And this is a pretty recent high definition ultrasound. You can see there's some pretty good definition here. Looks very lifelike. Sometimes students will ask, how do you get from this to this? Essentially, like with many things, there are a number of different transducers, and then signal processing is what allows images like this to be created from those arrays of transducers. Some pretty amazing images, though. Moving on, here is more what mechanical engineers usually use non-destructive testing for. This guy is checking for cracks in an airplane wing. Like it says down below, you can detect cracks in pipes, tubes, parts, wings, etc. You can detect bubbles, or you could 3D map pores down to 10 micrometer resolution. Once I was giving this lecture and I was suffering from a lack of sleep, well, that's what I'll blame it on at least, but I said detect cracks in pipes. I hope that you all get better jobs than that afterwards. I definitely misspoke there. Anyways, moving on. This is the procedure, and we are getting to an equation that you would use for ultrasound. Here we have that note from before, same thing, where we said for standard pulse echo, the wave must travel 2 times the distance between the transceiver and the feature, which is the density change or the change in acoustic impedance. So if we're using pulse echo method for height measurement, the first step, we send the pulse out. 2, we wait for the echo. So you might use an oscilloscope, or you might have a device that is going to show this or calculate this for you, measure this for you. But what you get there is the return time. So if you take that return time, multiply it times the speed of sound, and then take half of that. So really what you're taking is half the return time, remember, because it travels through it twice. And then the speed of sound, we can determine the distance it traveled. Or the more specifically, we would say the thickness of that part. So this is pretty important equation. This is something you could probably derive in your head pretty easily. Here's that example. I promised this will help to reinforce that. The problem statement is using pulse echo ultrasound to find cracks in airplane wing. So you are using pulse echo ultrasound to find cracks in an airplane wing. The specified thickness of the wing material is 5 millimeters. And the speed of sound, so C is what we use for the speed of sound. I forget the actual word, but if you go back to like Greek or Latin or something, let's think it's celeritas, like acceleration, velocity, that celeritas in there. That starts with C, so that's why we use C for the speed of sound. So the speed of sound, C, in the wing material is 5,000 meters per second. And the question here in red is, what time for a pulse to be received would indicate a crack? I'm going to walk you through the solution. What I would recommend, though, is pausing the video here and trying to solve this yourself. It'll help you to learn it, and come back when you're ready and we'll go through the solution. So now, of course, everybody did what I said, right? And now you're back. So let's go through the solution. So first thing we need to do is find the time it takes to receive the pulse if there is no crack. We're going to start with that equation that we were given, but we're going to need to rearrange it a little bit. We have the distance, or we're calling it the thickness. We have the speed, and we're after the return time. So we just rearrange all of that, the time. So time is equal to 2 times the thickness divided by the speed of sound. Pretty simple. Just plug things in and we get 2 microseconds. Now that we have that, we're ready for the second step. And the second step is just framing this to answer the question. We're asking, would a lesser or greater time indicate a crack? So we know it takes 2 microseconds for it to travel through the wing at its specified thickness without a crack and come back. Will a lesser or greater time indicate a crack? Think about that for a second. Pause it if you need to. Now you're coming back, and the answer is less time, right? If it takes those 2 microseconds to travel through and come back, then if the time is less than that, it means that it went through that crack, or went through that wing, and it ended up coming to a change in density or a change in acoustic impedance sooner, because there's a crack there. So it comes back sooner. So frame it to, like the question asked, we would say return time less than 2 microseconds indicates a crack. Then the last thing I wanted to show you, and we have 3 slides to show this, is that ultrasound can be used for material property determination. Here we have an equation for determining Poisson's ratio. So there's Poisson's ratio, which is the ratio, the negative ratio of the transverse strain over the axial strain. And to calculate that using the speed of sound, we would need to have the transverse or the shear wave speed, and we would need to have the longitudinal wave speed. So if we measured those 2 things, we could plug them into this equation and we could get Poisson's ratio. The next one is calculating Young's modulus. So Young's modulus is the constant of proportionality between the axial stress and the axial strain, sigma and epsilon. And this is equal to everything there we see on the right side of that. The key things are we need the longitudinal wave speed, so we use ultrasound to measure that. Here, so the material density is in there. Poisson's ratio is in there. We could determine Poisson's ratio from the previous slide, or maybe we already know that. And just having those things, we can determine Young's modulus. Then finally, shear modulus, G. So this is the constant of proportionality between the shear stress and the shear strain between tau and gamma. For this one, we just need to measure the transverse or shear wave speed and know the material density. We can determine the shear modulus. Of course, we can't have lab with with only having online classes due to the coronavirus. But we will be doing a demo of ultrasound, and these things would be something that we will likely have you do based on data we'll get you from that demo. More on that later. That's all for now.